Hello everyone, welcome to this very brief video, pun intended, on the Applied Maths project that has been recently implemented into the Applied Maths course. So what I have created here is a little booklet and will actually be part of my textbook once I release it, the second book, essentially just talking about how the project works and how to do your best. So all I'm going to be doing is just completely reviewing this particular chapter and kind of giving extra bits of information to people who are currently doing the project, or maybe if someone is done, if they want to use this as a guide to sort of review their project. So a couple of things. The start of these chapters, I always include what we're about to learn about. So info regarding the mathematical modelling project as set by the SEC, the modelling cycle, and then how we would go about presenting it. A couple of things to note is that you actually have to have a decent enough grasp of the course before you go ahead and start this project. That was kind of an error that the SEC made on the first two projects, having the project be due in February. So they're giving it until April, I think, in next year. So you have plenty of time to develop appropriate bits of the course to use in your project. It's also very Englishy, so you want to be able to have coherent sentences and sort of decent structure for your project. And as well, you need to be fairly proficient in preferably Microsoft Word, and I will explain what I mean by preferably once I go down here. So a couple of things to note about the project itself. The project is worth 20% of the grade, and the other 80% is for the final exam held. Usually the last exam is Applied Maths. Now, I do need to update this because it was February in 2024, but now it's being pushed to April. Still one of the earliest ones to be completed. So it is a bit annoying in that regard, but it is still plenty of time. Now, a couple of things to note on how to actually access the booklet in the brief. So I'm not going to do it here because hopefully these steps should be fairly okay to follow. So you go to goodoldexaminations.ie, and then down the side you have a thing called examination information. The section that you'd be probably most familiar with is examination material archive. It's literally the one that's directly above it. Then underneath examination information you should find something that says project and practical coursework or similar thereof, and find the one that says applied mathematics, and then the 20xx is just to substitute for your year. Then once you click on that, it should probably bring you to a separate page or give you a drop down menu, and once you click on the booklet in the brief, there should be a couple of files to click on. One that says applied maths, can't remember the actual name of it, but once you click it, it should start downloading a docx file. Now it has permissions obviously set, so you can't edit it directly, so you'd have to enable permissions for you to edit it. But one thing I would recommend is getting a copy of the thing that you download and edit it separately. Now with the SEC, Microsoft Word is the preferred word processing software, but if you use something like Google Docs, for example, because I know that's another alternative that some schools use, if you scroll down even further, there should be alternative links that should download a Google Doc file instead. Although I would recommend, if you're submitting it to a teacher, you can actually go into Google Docs and say to save as a docx file rather than a separate Google Docs file. Now, the project submission, this is one of the most common questions that have been posed a couple of times, because applied maths is one of the most popular subjects to do outside of a common timetable. Now, for me, when I did it, it was no bother. I pretty much contacted my school as soon as possible in order to make sure it got properly validated. So essentially what happens is that your subjects and the subjects you're assigned at school are up on what's known as an SEC portal. So you are assigned the subjects you were given by the school. And whenever you submit projects, you need to sign a thing known as a P20 form, which essentially signing off the fact that you did your project and no one else helped you bar your teacher. So there was no sort of outside help with your teacher. Now, as I say here, it's probably best to approach the school as soon as you can because there were exceptions in the first 2 years to say that a maths teacher would be able to supervise if your teacher did not have a qualified applied maths teacher for at least the old course. Even better if they're actually qualified for applied maths, it makes everything a bit easier, which it was in my case. However, you should, as soon as you get into fifth year, and if you don't get applied maths as one of your subjects, is to essentially free phone the SEC whenever you can. Now, their lines are pretty much up regularly enough, or you could send them an email to, I think, practicals@examinations.ie, I think is their email. Now, obviously, it's a very technical matter, and I'm essentially just completely parsing over the basics of it, but you should really contact your school and your principal, seeing if, firstly, if there is an applied maths class happening, if you could be registered under them, but take tutoring separately. Or if your school doesn't have an applied maths class, you should approach them even quicker to ensure that the SEC will recognise the fact that whoever's supervising your project does not interfere and doesn't give sort of any outside help. Now, it is very technical because if there's any sort of cheating or anything going on, you could be barred from state exams. I think the worst case is forever, but they could bar you for like up to 5 years. I'm no legal expert, that's kind of as far as I remember. And this actually includes your driver's license, which is considered a state exam. So all that legal jargon out of the way. A couple of other things. The conditions for the project are stated in the project brief. However, it tends to be about 800 to 1,000 words. So you're not allowed to write sort of superfluous essays about, oh, I did this because of da 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 da. You have to be very sort of direct in your reasoning and your discoveries. However, these 800 to 1,000 words do not account for equations, referencing, and data if you include any spreadsheets. The only caveat is that any images you contain, probably best to keep it either in terms of equations or sort of pictures of like graphs or whatever. If you include sort of extra words within the images, that might be considered trying to evade the word limit and might hamper your grade. Videos aren't included. So if you include a video, it's not actually going to play because they review it on a PDF software, and PDFs aren't necessarily good at trying to play videos. Another thing is that you have to ensure that the size of the PDF does not exceed a specific size. I forget what it was last year, but it's on the order of a few megabytes. Now that might seem really small, but considering there's very little words, and if you include in and around 5 or 6 images, that's only really on the air of about like 2 megabytes, so you're still grand enough. Now, another common thing that actually, very modern problem with all these current assessments is the use of AI. So it specifically says that you can use AI if you want to reference things, but you have to include the fact that you used either ChatGPT, Google Bard, or any other such AIs. Oh, it's called Gemini now, isn't it? So if you use either ChatGPT or Gemini, you have to quote it. There are a lot of modern AI detections, so if they detect sort of AI writing, they can sort of flag that and mark you pretty heavily. And yeah, as I said, if AI is used, you have to include it in your references. Now, references. Here's a common thing that the students ask kind of in general is how would I reference it at this level? Now, referencing in a Leaving Cert project is actually fairly different to how one would reference in an academic journal or if you're going for a master's or PhD. So in terms of what you have to reference and what you haven't, any formula that's already in common knowledge inside of the applied maths course, so I just picked centripetal force, Fc equals mr omega squared, that doesn't need to be cited. So if you use this, if you use the difference equations root theorems, for kind of the one that's done this year, that doesn't need to be quoted. If your notation is slightly different to how it is in your book, you might have to state that, because I used Fc instead of F, I would denote F sub C equals centripetal force in sort of brackets. And that also at least eliminates one extra word. But if it's any other bit of information, then you have to cite it. So this includes sort of census information if you're trying to gather that stuff. Now, there are a couple of ways that you can reference, kind of named after cities with big sort of universities with a lot of master's students doing a lot of referencing. Um, Kind of the common one is Vancouver referencing, which is the one that I actually use. It's also just called numerical referencing. But there are obviously other methods. So you can use the Harvard reference or Chicago reference. You don't necessarily have to state what reference you're going to use because a lot of these are already sort of at least ground enough and recognized as valid referencings. So here's just an example of how one would do a Vancouver reference. So in this case, moment of inertia is not on the course anymore, so I have to quote it. So I would say the moment of inertia for a solid sphere is found to be I equals 2/5 mr squared, where I is the moment of inertia, m is the mass, and r is the radius of the sphere. And then this little 1 would indicate in my references that this 1 would match with this little link here, which is just a little tool for calculating the moment of inertia of a solid sphere. So this would go in your section 1 where references is. So sort of in terms of what websites are best to reference, anything .gov or .edu is probably best. So here I have a .edu website, so it's fairly reliable. Kind of a common one for the .gov is NASA, because NASA is a governmental organization which puts out a lot of stuff related to physics. Not necessarily applicable for this year's project, but if you have one that has any sort of mechanics at least baked into it, NASA is a very good site to use. Another thing to include as well is the date that you last accessed the website, just in case the website doesn't work anymore. Now, obviously, you can sort of leave your project to the last minute and change all the date last access to that date. That's actually totally okay. Now, a couple of other ways to reference. You don't have to reference a website. If you take it from a book, then you still can. So here I have a cylinder moment of inertia, half mr squared, and I took this from probably the most popular, or one of the most popular physics, university physics textbooks, the one by Young and Friedman. You can include the ISBN if you really want to, or the page number if that sort of works in your favor. But this is fairly okay in terms of how to cite it. Now, the reason I have it italicized is just kind of by convention. If you're referencing a book or an academic journal, then you sort of put it in italics. Make sure to include the title and the authors. You don't have to include their first names if you don't want to. Now, genuine question that someone asked to me is that they had a great idea, sort of after the project date was gone. Obviously, no, you can't sort of beg the FCC to give the project back just to make tiny adjustments. One thing I do recommend is that if you have any ideas, jot it in like the back of a copy or something and sort of use that if you're going sort of working on your project. Now, another common thing to note, this is kind of parsing something else that I also received. A friend of mine knows partial differential equations, Stokes law, and other things. Will they get a higher grade? The answer is probably not. The reason is the level of maths has no determination on the grade that you get. So include partial differentials wherever you want. The kind of the bad thing is that you have to, first off, learn a lot more maths, first of all, because partial differential equations is like second or third year college maths type stuff, and Stokes law is in relation to differential equations, or at least the Stokes law in differential equations rather than the Stokes law in physics, which is to do with drag and all that kind of stuff. So what the project is actually doing is more so about your communication and how you sort of discuss how you get to certain parts of your iterations. And kind of the best advice is, because of the fact you're using a word processing software, please ensure you have autocorrect on, and at least if you're using Microsoft Word, you have the little editor so it marks off any of the really sort of esoteric and annoying grammar mistakes. So that's kind of all the information. One thing I will also have to do is this thing called the modeling cycle, and I will go through similar enough to the project that I did in 2024. So the modeling cycle is essentially just trying to make the problem more complex or more applicable to real life. So the first thing you do is you define or redefine your problem. So redefining is just introducing some new variables, which I will show you. Then you adjust what you have to actually look for, also known as the required parameters. Translate these parameters into mathematics, calculate the quantities, and do some bits of analysis. And then you repeat. So once you do this analysis, you might find that your answer is only valid for certain values, which is actually something that I have down here that we have to account for. Or if the answer is like egregiously large, then you have to find ways to sort of reduce that to a more applicable level. So a couple of kind of common ones, kind of 3 on mechanics and 1 on computation. Air resistance, kind of a common one. Rotational inertia, friction on pulleys, and computational time, which is known as big O notation. So if you're doing anything with algorithms, then you would probably have to mention that you want to get the computational time down fairly low. Obviously, you have to be creative with your iterations as well. You can obviously do sort of the bait ones of air resistance, inertia, or whatever, but you have to sort of be inventive in how one defines what air resistance might be. Because if you've done enough problems, especially in chapter 5, you might see that drag is often given as mkv or mkv squared, or in some cases mkv cubed, and sort of the constant the constant k will often change because of that. So it's just a couple of bits of advice. Now here is the one that I did. So I didn't actually copy paste my project. I kind of just parsed it ever so slightly and changed some of the diagrams as well. So this one was all about the design of particular parts of roller coasters, and the one that I chose was banked turns. So kind of if you're turning, but so essentially how it is that you're going around a turn, but your body is sort of angled relative to the ground. So the way it kind of goes is the introduction. So I just gave a little description with roller coasters and why, or sort of what I picked, and then sort of going in a bit more. So I did the safety requirements for these turns, assuming it travels at constant speed around the turn. So sort of what the maximum possible tilt is on any of these roller coasters. So in terms of key variables, so the mass of the rider and the mass of the coaster will remain the same, but what I'll be varying is speed, radius, and the angle of inclination as well. And then I threw my citations in here. So the first thing I did was sort of set out what roller coaster I'd actually be basing off of. Now, because I am a Meath resident, I chose Cuchulainn in Emerald Park, formerly Tato Park. So I did actually retitle it Emerald Park because at the time I was doing it, I think I called it Tato Park when it was kind of transferred by that point. Little details about that, like, it won't cost you anything. It's grand enough. So there are 24 carts on the coaster with a mean mass of 735 kilograms, again including the citations, accounting for total mass of 35,280 kilograms. I also said the radius of the turn is r and it's angled at alpha above the horizontal, and here's the free body diagram. Another thing, if you don't know how to include your sort of little notes like figures, then that's something I would probably learn. It doesn't take too much. It's only a couple of clicks. Now, I did also make a few errors in here where that I should fix. I think I called big R sort of little r in a couple of places and called the reaction force R when I wanted to call it N. Now these diagrams, I kind of rushed them because I was rushing to kind of get this at least done. I guess you can sort of define your variables like I did with capital R, but you can write them in words if you want. But you also have to state if you ever change it, like N is reaction force or whatever. Okay. Then, yeah, so I called it N in this case. So by letting the reaction force be N, we can say, and then it's just a couple of things. So W is mg is also a quote down here. So N sine alpha is W, and N cos alpha is mv squared over capital R. And then after doing a bunch of manipulation, we arrive at a familiar result that V is just the square root of GR times the tangent of the angle alpha. So as well in here, you don't have to quote that. I think I made a mistake here. Mg over sine alpha times cos alpha. Did I make a mistake here? I think I did, because sine over cos is tan, so I think I must have made a mistake here. I'll fix it later. Because if we just mg over sine alpha, then we get here as over tan alpha cancelling. Yeah, okay. I think I made a bit of a mistake here. Yeah, because n cos alpha is w. So sorry, I mixed up those angles there. Now, I actually did make a very quite egregious error in when I was doing my project and didn't notice it till after, and I didn't get docked a lot of marks. So sort of slip ups there will be counted like a slip in maths where it's only necessarily 1 or 2 marks. So that should be n cos alpha and then sine alpha instead of that way around. Now, one thing as well is that I know I kind of didn't show it here, but sort of skipping a lot of steps is not very good manners. So if you just say, "Oh, I got to this result," it's trivial. It doesn't really help your wording of things. Now, anything I sort of put in brackets is just kind of advice and not necessarily something I'd push in the project itself. One thing I did include is that the occupant must be experiencing less than 49 meters per second squared. I should have included a citation there as well. So a lot of these are trivial in a sense on how to get a tan alpha is less than 5, because at that point you're manipulating a simpler equation. So I also denoted AC is the centripetal acceleration, because we know that AC is just v squared over r, so it's just the force divided by mass in that case. Now, the next thing I included was eccentricity. So this is a thing actually in elliptical geometry, where we talk about sort of how similar an ellipse is compared to sort of a standard circle. So we can approximate the radius of a circle at any point by just mapping, the radius of an ellipse by mapping it to an equivalent circle. Now, I kind of did phrase this very specifically and very much like a scientist. So I'd say I opened Google Maps, took some measurements, and estimated from the center of the circle to that. And this is an actual image I included within it. So I took some Google Street View stuff, zoomed in on this particular banked turn, which is actually banked rather heavily, and took some estimates of where the center of the relative circle would be and used the measure distance tool to find that distance. Then after that, I included a table. I'll always sort of title your tables. And then here's a bunch of information. So x bar and y bar, they're common enough notations to mean the average of x and average of y. So we don't need to necessarily quote that x bar is the average and y bar is the average of there. Then after doing a bit of calculations, I found it to be about 0.77-ish. The kind of mistake I did make is that this should actually be like a 1 plus e, more so than just an e. Mostly for the fact that for a circle, the eccentricity is 0. So we actually end up getting a math error if we plug in e equals 0 in this case. But I sort of did make the argument that a perfect circle essentially cannot be constructed, and it's not something we necessarily have to account for. Now, the final thing I included was the drag force. Again, something I should have cited because it's not necessarily something you covered. But here's the form that's on the NASA website as a half rho v squared c sub dA, where obviously I state all of the variables. That's something I should have done, and the coefficient of drag for a flat surface is about 1.38, again from NASA. Then the maths here might seem a bit complicated, but what I'm essentially saying is that the net force is equal to the square of the net force is equal to the square of the centripetal force plus the square of the drag force, because if we draw diagrams, centripetal force acts inwards, the drag force acts directly back on the rider, so they will be naturally perpendicular, so the net force will just be using Pythagoras' theorem on them two, and then subbing things in here as well. So the centripetal force will be mv squared divided by the radius, which will just be the eccentricity times the radius. Then after doing a lot of simplification, we get to v equals 6.1 root r, and then because we know v is GER tan alpha, we can make this substitution that the tan alpha is actually less than 3.8 divided by e, which is slightly more restricting. Now, the interpretation of the results is the last section, so you just talk about all the stages, how you arrived at the end stage, and how that maps with essentially what you've discovered. So I found that top speed is about 25 meters per second, which would imply that the radius is about 16.8 meters at the average of a 16.8. Now here, I obviously got it to be about 40 in some places and 20 in others. So I sort of did make the assumption that because it's wooden, it might actually slow the ride down a lot more. And on sort of lots of energy. Because if you've ever been near Cuchulainn, you'll note that it's incredibly loud with all the reinforced wood and steel kind of clanging off of each other. So I have a couple of ones here if you sort of want practice, especially if you're in fifth year. So there's one about airplanes, there's ones about marathons and optimization, pulleys, altitudes, then talking about sort of new civilizations, some visa stuff there, bike lanes, difference equations. Newton's law of cooling is kind of a popular one in my book. I think I have like 4 questions on variants of Newton's law of cooling. Delivery services, infections or diseases. Obviously very apt one now. Trust structures kind of would favor all the engineers. That's in probability. Algorithms for cybersecurity, kind of all sort of fairly apt projects, as these are kind of very essentially modern problems. But then I included some ones like exploring mathematics and cookery, holes in ones in golf, and even stuff like music theory. Yeah, it can also be included there. So that's essentially just a rough guide on how one would go about the project. So if you have any questions, please do comment and I will try to get to you as quick as I can. Cheers.